I think I can start. So I switch the schedule again with the teaching assistant because the rest of the exercises needs the stuff that I will talk today. And although there are still only 2 remaining exercises, but these 2 are more technical. So yesterday, we talked about a few examples for the applications of the heavy quark spin and the heavy quark flavor symmetries. So let's continue with the example that we started already yesterday, but we only started only a small part, right? Now we consider the S-wave scattering between a pair of H means D or D star, and H bar, D bar or D star bar mesons, right? Of course, here, although I write D star or B bar, B star bar, it also means the same formalism you can of course use to describe the interaction between B bar, B star bar, right? Here, from here to there, you simply replace your charm quark by bottom quark, right? And here, then you would have B and B star, right? And of course, if you think more, because we also talk about this heavy anti-quark diquark symmetry. Here, this is heavy quark flavor symmetry. You can even extend or use exactly the same formalism or exactly the same relations that we can derive to the system by replacing the heavy quark by anti-heavy diquarks. Right? So you can even go to this cascade QQ, right? Heavy anti-quark diquark symmetry, and it's a spin polarization, right? The ones that belong to the same spin multiplace. And here, of course, you can go to QQ with a bar. Okay. So basically, you have many different combinations, but all these relations are very similar or even exactly the same. Okay. For now, we simply take D star and this D bar, D star bar as an example. Okay. Yesterday, we listed that these mesons, we can group them into different pairs. They have different GPC, right? So 0 plus plus, if you remember, 0 plus plus contains what? Contains which meson pairs? D bar, right? And D star bar, right? So because we only consider S-wave, so this positive parity comes from we are considering only the 0 orbital angular momentum, because we are considering a pair of mesons. So the parity is simply given by -1 to the power L. L here for S-wave is 0. And the C parity comes from -1 to the power L plus S. But this is only for pairs of particle and anti-particle, right? Particle plus its anti-particle. So it's exactly used for a given particle and its own anti-particle. Okay. So we are considering here D star and its anti-particle D star bar. But things becomes different, right? If we consider D and D star, D star bar. Now you see, although this one is a charmed meson, this one is anti-charmed meson, but this guy is not the antiparticle of D, right? Because this is D star bar. This is antiparticle of D star. So So for this pair, we cannot use this formula. We cannot use -1 to the power L plus S. What we use is that we first give some phase convention for the charge conjugation of this charged meson. Right? We choose phase convention for charge conjugation. Because this is convention, so this is up to our choice. Right? So we can choose either positive or negative, doesn't really matter. So the phase convention that we choose is D and C parity becomes D bar, and D star becomes minus D star bar. Okay. So for this kind of stuff, this should be understood as D0 becomes D0 bar, D plus becomes D minus. Okay. Now, if we choose this phase convention, and then this negative C parity would correspond to, there is a relative positive sign between D star bar and D bar, D star. Of course, we can normalize this by putting one additional square root, 1 over square root 2. But let me put some side mark here. Here, I haven't mentioned about the iso spin, right? But each D and D star, they are iso spin 1/2 mesons. Right? So a pair of D and D star, or each of these charmed meson pairs, they have two different iso spins. For instance, iso spin 0 and iso spin 1. Okay. For instance, for the DD bar pair, what are these iso spin combinations, right? For the D, then the iso spin would be D, C, or CU, well, we put the CD bar, CU bar, okay? D plus, D 0. Okay? And D bar, we would have C bar, C, okay, we can write C bar U, C bar D, right? We would have D0, D plus. So we have this kind of pairs. So iso spin 0, what we would have would be 1 over square root 2, D0, D star bar 0 plus D minus. Of course, actually, if you write down this iso spin wave function, you can simply choose. Here there is also a phase convention, but here we simply write in. I think let me see, D bar. Yes, we maybe let me just split the steps. Okay, we can write in this way. Iso spin 0 for two iso spin 1/2 particles, their iso spin wave function is what? Is symmetric or anti-symmetric? Two iso spin 1/2, they combine into iso spin 0. It's anti-symmetric, right? Now we use this upward, downward, minus, downward, upward, right? Something like this, okay? So now this one, for instance, this one I would call this D plus, D0. And then the first one I refer to the D meson. The second one I refer to the anti-D meson. And then this one I would write this as D0 bar. And then this one I will write D plus and D minus. But here there is also a phase convention, which we normally choose the minus D. The relation is we normally choose is the one with the negative with anti-D quark. We require this to be minus iso spin 1/2, iso spin third component equals to 1/2. All the others we just use plus. This means this is for anti-light quark, and then U bar, and then we write this as positive, I is being 1/2, I is being third component is to minus 1/2, okay, Q bar. Now, this one, this D bar, which corresponds to this D plus, there is this kind of minus sign here. So this introduces minus sign here, right? So finally, what we get is 1 / square root 2 D0 D0 bar plus D minus. Okay? This is also being 1/2, also being 0 combination. So each of this pair, this D bar pair, if we write up explicitly the particle basis components. These are the particle basis components, D0, D plus, D0 bar, D minus. And then it is split into these two terms, right? And then for the acyl spin 1, we would have a different, for instance, a question? Okay, so for the acyl spin 1, if we consider acyl spin 1 and the acyl spin third component equals to 0, this one, and then that would be 1 / square root 2 D0 D0 bar minus D plus D minus, okay? So it's, because they are orthogonal to each other, there must be some relative sign difference, right? So each of these pairs, if we write them down in particle basis, each of these pair actually now becomes this kind of a similar expression, right? Or also this one, that one, they all becomes a similar combination of two terms or superposition of two different components, right? In total, for instance, this one, you would have, you expand this completely, you would have 4 terms, right? And then this 1 / square root 2, here another 1 / square root 2, you would have 1 / 2, and then 4 terms, and then this is still normalized. And then we also said this D star bar, for the total spin to be 1, the C parity is again negative, right? Because they have, for S wave, they have orbital angular momentum vanishing, 0. And then the total spin is 1. And then minus 1 to the power 0 plus 1, that's a negative. So that's why D star bar is put here. And then we have 1 plus plus. 1 plus plus. So the difference is compared to this pair, the C parity is different. And then we have 1 / square root 2 D star bar minus D bar D star. Okay? And then these two pairs have different C parity. And then D star bar, for the total spin 1, they don't have this positive C parity component. That's why it does not appear here. But it has 2 plus plus, then D star bar, right? 1, 2, 3, 4, 5, 6. So we have 6 pairs for each iso spin. But we already recognize the one that I introduced yesterday, the famous particle X 3872. I also said its quantum numbers GPC equals to 1 plus plus. Okay, 1 plus plus is here, right? Corresponding to this line. And its mass is close to D star bar threshold. So its dynamics should have received some influence, at least, from the D star bar S wave interaction. Or in other way, so the S wave D star bar scattering must contain information of the X372 because it couples. And then you as long as two hadron couples to some resonance, and then as long as you can build general enough scattering amplitude for these two hadron, and then all the resonances that can decay or couple to this meson pair must be you must be able to produce that resonance, right? That's it's a general statement. And then this ZC 3900. I think yesterday I didn't give the JPC quantum numbers. Now I refer to the neutral component inside this isospin triplet. Okay, the ZC has isospin 1, so it has positive electrically charged and also negatively electrically charged and also neutral one. And only the neutral one is flavor neutral, right? It does not have any net flavor quantum number. So only this guy has given C parity. Okay. For this guy, the GPC quantum number is known. It's 1 plus minus. Okay. It decays into J psi pi. Okay. Pi 0, for instance. So the G parity of this pi is what? G parity. G parity of pi. Do you still remember? Please. Yes. And G parity of deep psi. It's -1 to the isospin of deep psi. 0, right? Times C is also negative. Excellent. This is -1 to the power isospin, multiply the deep psi C parity is negative, right? This means this ZC, the ZCG parity is positive, right? The G parity is just the products of these two, the G parity of these two guys is positive. And then the ZC 4020, 0. This one decays into HC pi 0, okay? For HC, the HC quantum numbers, HC, JPC of HC, who knows this? Equals to what? You know what HC is? HC is a p-wave harmonium, okay? For p-wave harmonia, we have several p-wave harmonia. Okay? P-wave means the orbital angular momentum between CC bar pair is 1, right? The CC bar total spin can be either 0 or 1, right? If we consider first the total spin of CC bar pair to be 0, and then this couples to LCC bar to the orbital angular momentum, what we have is the total spin of the CC bar system is 1, right? And this one, we will get 3 different combinations. This one couples to another one, we get 0, 1, or 2, right? And then the parity for this guy, because that's p-wave, and it's a p-wave for a pair of fermion, anti-fermion, so it's -1 to the power L plus 1, so it's positive, right? And the C parity for this guy is -1 to the power L plus S, it's negative. This corresponds to HC, 1 plus minus. Okay? And here, again, this parity is positive. And C parity now becomes opposite compared to this guy, because the total spin of CC bar pair now becomes 1. So 1 plus 1 is an even number. So now this C parity becomes positive. These are called chi C0, chi C1, and chi C2. Okay? We also call this as a spin triplet because we have 3 of them. Spin triplet of p-wave heavy quarkonia. Spin triplet. Here, since we have only one, it's a spin singlet. Okay, this is a spin singlet. Okay. But again, the C parity of this guy is negative. The C parity of pi 0 is positive. So the C parity of this ZC is also negative. So it has the same quantum number. GPC equals to 1 plus minus. And G parity of this ZC is also positive. And similarly, the ZB. Okay, I think I would use this very small space. Similarly, ZB 10, 610 and ZB 10, 650. Because they are very heavy, so their Compton wavelength is smaller. So I can squish them into this smaller space. So they're much heavier than the charmonium state. Okay, charmonium-like state. So these are the systems that we are interested in. Now we see whether we can get qualitative conclusions without doing any complicated calculation. Okay. We can derive some selection rules. From the knowledge of the spin coupling. Okay? From spin couplings. Or from heavy quark spin symmetry. The selection rules would be exact in the heavy quark limit. Okay. Now, how can we do this, right? So in the heavy quark limit, what are conserved, right? We need to first know what are conserved, and then based on what kind of quantum number, we can derive selection rules. Let's just review again. In the heavy quark limit, the conserved quantities, the conserved angular momentum becomes the angular momentum or the total spin of CC bar pair, right? And the orbital, the angular momentum of the light degrees of freedom, right? Because we have a total angular momentum conservation. Now we said in the heavy quark limit, the spin of each heavy quark becomes conserved. Its spin polarization is the direction of the spin pointing to some direction. This can never change. The spin cannot be flipped because any spin dependent interaction is suppressed by the momentum scale carried away by the gluon over the heavy quark mass. So for all the reactions involving a soft gluon, or if the momentum scale of the gluon which attaches to the heavy quark, if the momentum is much smaller than the heavy quark mass, and then you always have this heavy quark spin symmetry as a good approximation, right? Consequently, we have now two separately conserved angular momentum, right? This one is the total spin of C bar pair. And this one is the total angular momentum of the light degrees of freedom, which includes spins of Q bar, the light quark pairs, and orbital angular momentum. Orbital angular momentum, okay? But here, we have particles, right? The particles, they are in a different basis. For instance, the D for particle basis. We have, for instance, D, okay, which is CQ bar, right? We can write this in terms of the spin of the charm quark and the angular momentum of the light quark as SC. If you consider this as the first particle, SC1, and then this, the light quark in the first particle, SL1, okay? And of course, they have total dG1. G1 means the spin of this d equals to 1/2, right? This equals to 1/2, this equals to 1/2. And then if we consider another one, it would be d bar. Just take as an example, right? This would refer to the d bar pair, but all the other pairs, you can do a similar analysis. And this one, we will call this as particle 2, right? Then we can write this as SC2, SL2, G2. All of them, of course, also equal to 1/2. Please. This total angular momentum. This is total angular momentum. Total angular momentum. Or the total spin of the spin of the meson. It's not the third component, okay? And all of them refers to the spin of that particle. I don't talk about the third components here. Okay. Now, yeah. Oh, sorry. Very good. Thank you. Right? I made a mistake, right? This is the spin of d is 0. This is another 0, right? If this is d star, and then of course this is 1. Thank you. But all the other students, why couldn't you point this out? I will give additional points in my classes for any students pointing out my mistakes. Okay. Now, we have, if we want to use this new good quantum numbers, and then we need to recouple all these spins of the quarks, right? We need to recouple them to the total spin recoupling to the total spin of the CC bar pair and the total angular momentum of the light degrees of freedom, right? Which refers to the light quark, light antiquark, and an orbital angular momentum. But we are in S with H bar pair, right? Now I use H to collectively call this d star S with pair. So the orbital angular momentum here is 0. And d and d star, they are all S with mesons. So the orbital angular momentum inside the meson, they are all 0, right? We don't have any orbital angular momentum. So what we consider are just this, the total spins of the light quark antiquark system and the total spin of the heavy quark antiquark system. Now, we can consider this C bar pair. There are only two possibilities, right? Just as pointed out by the student, by the audience, this must be 0 or 1, right? We have 2.5 particles, and then it could be 0 or 1, right? And then we label this PC to be the parity and C parity of the CC bar pair. For this one, what is PC for this guy? For the spin 0 combination, what is the parity? Please. Yes. And C? Yes. And this one? Thank you. Excellent. Right? So for S3, we would have 0 minus plus and 1 minus minus. These are exactly the quantum numbers you have for the ground state pseudoscalar meson and ground C vector meson because they are S with QQ bar mesons. Right? You have these quantum numbers. And then this S QQ bar PC, because now again everything are in S wave. And then it's very similar. Now it's 0 minus plus, 1 minus minus. Okay, I put this CC bar, QQ bar, QQ bar for clarity. Okay. Now we consider the coupling of this pair to that pair to see what kind of combinations that we can have. For instance, first we consider S QQ bar PC equals to 0 minus plus. Okay. Now I couple this to the SCC bar. Okay. This couples to SCC bar PC equals to 0 minus plus and 1 minus minus CC bar, right? Now, this leads to, we consider this pair, right? Well, what would you get? 0 minus plus and 0 minus plus. What would you get? As a total, now would be the GPC, right? The G would be the total angular momentum of the whole system of a CC bar and a QQ bar. Right? 0 minus plus, 0 minus plus, 0 and 0, you couple them, of course you still get 0. P and C, they are multiplicative quantum numbers, right? Minus, you get plus, right? Plus, you get again plus. Now this one couples to this one, okay? Couples to 1 minus minus. You would get 1, right? 0 couples to 1, you get 1. Parity, negative, another negative, you get positive. Negative, positive C parity, negative C parity, you get negative, right? You form these two different possibilities. And now we consider this, the first case. Second case, SQQ bar PC equals to 1 minus minus. This couples to SCC bar PC equals to 0 minus plus CC bar, 1 CC bar minus minus, right? We get JPC equals to 1 minus minus, 0 minus plus. Again, we have 1 plus minus, right? But then you couple this 1 minus minus with this another 1 minus minus. We have what? What would we get, right? 1 couples to 1, we have 0, 1, and 2, right? All of them have positive parity, positive C parity, right? And this would qualify as a, well, I think we just leave in this way. But here you see we already classify different groups of the GPC quantum numbers. What you find is that the quantum numbers for the XA72 appears only here, right? 1 plus plus is here. It comes from the CC bar pair spin equals to 1. The light quark pair spin equals to 1, right? As I said, these two are good quantum numbers in the heavy quark limit. This means in the reactions, in the case of Xa72 into any timonium, for instance, into deep psi or eta C or this kind of stuff, it needs to obey some selection rules. The selection rules are only those which conserve this kind of these two quantum numbers are allowed in the heavy quark limit, right? And then we will find if the X is kind of hadronic molecule, whose dynamics is completely given by the S wave d star scattering, and then we find that the selection rules for X decays which the consequence of this actually is in a paper by Misha Voloshin in probably 2004 or so. You will find this Xa72. It can decay into deep psi pi, for instance, deep psi pi plus pi minus, because the deep psi CC bar spin is 1, but it cannot decay into eta C plus light hadrons, right? Because eta C, the spin inside eta C for CC bar is 0. It's different. It's not allowed in the heavy quark limit. It cannot decay into HC plus light hadrons, right? Because I just explained HC, the spin of this total spin of CC bar inside eta C is also 0, and it can decay into chi CJ, for instance, plus pions. Okay. These are allowed, these are not allowed. These are the selection rules. But again, we notice that we have two different 1 plus minus, right? We have two different 1 plus minus. We had indeed two different 1 plus minus states. We have one, the ZC 3900, another one is ZC 4020. If in the heavy quark limit, there is Xa72, or its heavy quark is in the heavy quark limit, or its heavy quark limit analog becomes a hadronic molecule. And then the Xa72, from here, we can conclude it must have 3 additional partners, okay, in the heavy quark limit. Heavy quark limit. The 1 plus plus hadronic molecule, which hadronic molecule, I think I didn't explain this concept. This is a composite system composed of a pair of hadrons, just like the neutron is a bound-state proton neutron. But you just think you just replace proton neutron by some other hadrons if they have enough attraction, and they can form composite system, right? And then this D and D star bar, they could have a strong attraction to form this kind of hadronic molecule. And then what the statement is, in the heavy quark limit, as long as there is 1 plus hadronic molecule, it should have 3 heavy quark spin symmetry partners, spin partners. How did I derive this conclusion, right? That is because this group has a given quantum numbers of this light quark, anti-quark system. And although they have different CC bar spin, but as I said, in the heavy quark limit, the heavy quark spin just decouples from the system. It doesn't matter what kind of CC bar spin you have. You see, the spin 0, spin 1, they do not make any difference, right, in the heavy quark limit. Although the heavy quarks, they are spin when have particles, but they act just like they don't have any spin. So it doesn't really matter whether their total spin is 0 or 1. They have the same dynamics. But really, what really matters is the light degrees of freedom. If they have different angular momentum for the light degrees of freedom, and then their dynamics would be different. Okay? From here, we can conclude there are two different spin multiplets corresponding to SQQ bar equals to 0 and 1. Okay? For each isospin, right? Because isospin 0 and isospin 1, they are not connected. If we only consider the SU2, they are not connected. And then for each isospin, we have two spin multiplets. Okay? In total, because we have two isospins, then in total we have 4 spin multiplets. Now, this is in the multiplet that isospin equals to 0, because we said this we consider this X to be isospin scalar particle, and then SQQ bar equals to 1. Okay. And if both ZB 10, 610 and ZB 10, 650 or the ZC 700 and 4020, they are hadronic molecular states, or if there are two 1 plus minus hadron molecules from the given isospin, does not matter which one that is, from the given isospin, and then there must be additional 4 states, right? Why there's additional 4? That's because then there should be additional 0 plus plus, 0 plus plus, 1 plus plus, 2 plus plus. If both 1 plus minus, they form hadron molecules, and then you should have additionally 4 other partners. Okay? Then there should exist four additional states, right? So without any explicit calculation, we can already conclude this, right? We already conclude the number of states and their quantum numbers. And then with the quantum numbers, we can already, if we are experimentalists, we can already try to search for them, right? We can guess their masses, because their masses must be close to the corresponding thresholds. And then the quantum numbers help us to know in which final states we should look for. We should look for them, right? So if isospin equals to 1, okay, and then that will correspond to ZB 10, 610 or ZB 10, 650. And their partners are called, their partners are named by Misha-Voloshin. Again, by Misha-Voloshin. WC0, WC0 prime, WC1, WC2. This corresponds to these 4 different pairs. Okay, that's GPC equals to G plus plus, azimuth spin equals to 1. For instance, now this guy, so azimuth spin 1, right? The GPC is exactly the same as X3872, but azimuth spin is different. So this guy can decay into, well, because they are ZB, okay, I should write this as B, B, WB, right? And this one can decay into epsilon pi plus pi minus, without breaking any symmetry. Now this pi plus pi minus pair, because I think yesterday in the exercise you would already know, this pi plus pi minus pair with a negative C parity, they must be also vector. Now we can reinterpret the same as atlas results on the epsilon pi pi analysis, the negative results of any observation of a resonance as they have not found a signal of WB, right? As no signal so far. For WBJ states, okay? So if they find something, it would not be the XB, it would not be the bottom partner of the X72, but it's the partner, the spin partner of the ZB states, okay? Because this decay does not break azimuth spin symmetry, but the XB decays in epsilon pi pi would break azimuth spin symmetry. That would be heavily suppressed. Any question up to this point? Yeah, please. Not yet. There were papers quite a few years ago trying to search for XB, that's the bottom partner of the X372, in the final state epsilon pi pi, but they did not find any signal. So the interpretation would be, because the XB decays into epsilon pi pi, that is azimuth spin breaking. Because this one is azimuth spin vector final state, but XB is azimuth spin scalar state. And in that case, there is no good reason as the azimuth spin breaking for the X3072, and then such decay would be really highly suppressed. But here, the WB states, their decay into epsilon pi pi is not suppressed by anything. So their negative signal could be interpreted as so far there were no signal of the WBJ states or in their hadron, in the proton-proton collision analysis. But that could be in the future, right? We cannot conclude they do not exist. For the diquark, actually I didn't talk about the diquark, but for diquark, anti-diquark, we can do similar analysis, I think. So for this spin, the spin structures, I think everything just holds, right? Because for the diquark, anti-diquark there, you also have the light quark spin, the heavy quark spin. Up to this point, I would see all these structures are the same. If we do not go into the next step as interpreting of what state is diquark, anti-diquark, tetraquark, or is a Henry molecule, but the spin structures, they're all the same, because here, up to this point, I have not touched about the internal structure, right? As with spin 0, up, down. As with spin 0, that would be up, down. What do you mean by up, down? Yeah. Of course. As with spin 0, of course, that would be up, down, and so it would be up, up D bar, up, down, up, anti, down, and anti, up, down, right? Something like this. And then it's different. It's a different system, right? That would be double bottom system. It's not the hidden bottom system, right? That would be different system. But that system, then this PC, this PC analysis, the C parity analysis doesn't hold because there is no given C parity for this kind of double bottom system because they are not flavor neutral systems. But the parity holds, but there is no C parity for that system. But all the spin analysis, they are the same. Any further question? Okay. If not, then let's go on. Okay, I think I can erase this part. Now, how can we do realistic calculation, right? So far, we have not touched upon any calculations. They are all qualitative analysis. But of course, we can do more quantitative calculation. But this requires us quantitatively. This requires us to solve, for instance, Schrodinger equation. Yeah. Yeah. Yes. Okay, I think so. Yes. Thank you. Then, if you have questions, you can still discuss. Okay. So before I go to the qualitative derivations, there's one more point that I want to make. Okay, from here. From this, so to say, classifications, you see here there is 1++ and 2++. Okay, both 1++ and 2++ only happen here. Okay, so from here you can already conclude this 1++ and 2++ pairs corresponding to the meson pairs that are already erased. This 1++ is D star bar. 2++ is only D star bar. Their interaction in the Havelock limit should be the same, right? But the others we cannot conclude immediately because here we have two 0++, and we have two different 0++ meson pairs. We have D plus D bar. We have D star bar. These two are linear combinations or superpositions of DD bar and DD star bar. These two are linear combinations of the D star bar and the negative DD star bar composition, right? But this one is purely DD star bar with positive C parity. This one is purely 2++ D star bar. Okay, and you can derive explicitly this is indeed the case. Okay, how can we do that? So the explicit derivation, I think Teng can tell you in her tutorial, or Xiangkun, I don't know how the tasks are distributed, up to them. But here, just to give you the idea how this can be derived. Okay? Now, we consider meson pair. Okay? H bar pair We call this as particle 1. We call this as particle 2. Right. Now, in the spin basis, we have for particle 1 SC1, SQ bar 1, G1, right? That's for the spin of the C quark in particle 1, the spin of the light quark in particle 1, or light or anti-light. It doesn't matter. So you know what I mean. Okay? And the spin of the particle 1. And then SC bar 1, SC bar 2, SQ2, G2. These are the spin of the heavy quark inside particle 2, the spin of the light quark inside particle 2, the spin of particle 2, right? But I want to express this in terms of SCC bar and SQQ bar, because only for the SCC bar and the SQQ bar, we have them as good quantum numbers. We can derive relations from heavy quark spin symmetry. Okay? So this means we can just insert a complete relation, right? A completeness relation. Then the completeness relation is just we make a unitary transformation or orthogonal rotation or in this spin space. Now we write as C1. So we just recouple all these. We have 4 different angular momentum, right? We have 4 different spins. We just recouple them. Okay. Now we first couple SC1 and SC bar 2 to SCC bar. Okay. SCC bar. And then we couple SQ bar 1, SQ2 to SQQ bar. Of course, the still I can write this again, the capital G. They couple to the same capital G, right? Now the complete relation is formed in this basis. SC1, SC bar 2, SCC bar, SQ bar 1, SQ2, SQQ bar, J. Okay? And we sum over all the possible, states that you formed under this basis. This means we need to sum over the newly introduced this recoupled spins, right? This is the total spin of SCC bar and the spin of SQQ bar. We sum over all their possible values, right? And then, of course, we insert this completeness relation, right? Because this guy equals to 1, right? Insert in front of this. SC1, SQ bar 1, J1, SC bar 2, SQ2, J2, J. Now you recognize this. What is this? That's a Clebsch-Gordon coefficient, right? That is CG coefficients. Now we have these CG coefficients, and then the CG coefficients is multiplied by this basis state. And then we sum over all these possible, we make it, or so to say, we make an expansion of these states in different bases, right? And then the expansion coefficients for the expansion is given by the CG coefficients, which comes from recoupling of the spins or the orbital angular moment, or the recapping of the angular momenta. And this CG coefficient, this is CG coefficients. This given is CG. I use CG to represent this. It can be written in terms of the Wigner-Nijin symbols. Okay, Wigner-9J symbols, which you can compute using Mathematica. This equals to square root 2 G1 plus 1, 2 G2 plus 1, 2 CC bar plus 1, 2 S QQ bar plus 1, and comes to the 9J symbol, which is SC1, SC bar 2. For instance, this SCC bar, this line, these two guys couples to this one. Okay, and here I have S Q bar 1, S Q bar 2. Here SQ2 comes from SQQ bar because these two spins couple to SQQ bar. And now this rows, these two, the SC1, SQ bar 1, they couple to the spin of the first particle, right, G1. These two couple to the spin of the second particle, G2. And either this or that, they couple to the total spin, the total angular momentum of the whole system, right? It's very easy to memorize. So because you just put all these angular momenta together, and then you just couple them. And then in this way, you rewrite this CG coefficients in terms of this 9J symbol. This you can compute from Mathematica easily, right? And then in this way, you can derive the relations. For instance, you can derive, for instance, D bar goes to D bar, also spin 0, okay? For instance, for this one. How should I derive this? So I will write D bar also spin 0 as 1/2 1 over square root 2 D0 bar plus D minus, right? For instance, now I focus on D0 bar goes to D0 bar. Just to give you example, right? I call this as particle 1, this as particle 2, another particle 1, another particle 2, right? And for this one, that would be, for this guy, that would be SC1 equals to, I would write this in this way, okay? SC1 would be 1/2, right? Now I put that C1, okay, to have explicit correspondence to that notation. And then here, it would be 1/2, which comes from the light quarks, Q bar 1, and then their spin, of course, is 0, not 1/2, right? That's for D0. And this guy is the spin of C quark is 1/2, C bar 2. So this one is this. This one, this one. Then 1/2 Q2, and the total spin 0 for D bar 0, right? And of course, in S wave, their total angular momentum is 0. So this way, I rewrite this meson pair in terms of the notation I put here, right? And of course, the final state, you can again rewrite in terms of this in the same way, right? You just put them together, So what you would have would be the D0 bar in the final state, and some interaction, I call this V hat, right? And D0 bar in the initial state. And then finally what you would get would be some something depends on the 90 symbols, and the 90 symbols I simply write as or the CG coefficients I would write as CG1, okay? And then you would have something like SC1, SC bar 2, SCC bar, and SQ1, SQ bar 1, SQ2, SQQ bar, J, V hat, right? And then another pair. Now, see whether this I initial or final. Another pair I could put is SC1 prime, SC bar 2 prime, SCC bar prime, and then SQ bar 1 prime, SQ2 prime, SQQ bar prime, and capital G. G is always conserved, or we can again put this as a prime, for instance, right? And we need to sum over this. Okay, I put this as okay. This, you know what I mean. This is CG coefficients. Sum over SCC bar, SQQ bar. Although I put here there are and then SCC bar prime, SQQ bar prime, all of them, right? But this stuff, we have good quantum numbers. These good quantum numbers must be conserved. We have this must equal to the one in the or in this I call this as capital A. Okay, we would have this capital A must equal to delta SCC bar prime, because this is conserved, right? And delta SQQ bar and SQQ bar prime, because this is conserved. And of course, the G must be conserved, right? And then we would have everything just depends on the rest, and also we have the system does not depend on the total spin of the heavy quarks. The dynamics do not depend on the spin of the heavy quarks, because they decoupled, right? Does not matter whether the C bar pair spin is 1 or 0. They all give the same dynamics. So what the dynamics depends on is just the light quark spin part. Okay, we would have SQ bar 1, SQ2, SQQ bar. I neglect this J. Okay, probably here is better to avoid confusion. I simply put this J because this is always conserved. Then I don't need to write this guy, right? Because the total J is always there. And then the potential, and SQ bar 1 prime, SQ2 prime, S Q bar prime. Right? All the other stuff that the dynamics do not depend on, I didn't write them explicitly. Right? In principle, you can also put this SC1, SC bar 2, SCC bar on both sides, and you have different SCC bar. You have SCC bar equals to 1, SCC bar equal to 0. But the system does not depend on the value of SCC bar. Also to see, the metric element for SCC bar equal to 1 is equal to the metric element for SCC bar equal to 0. Okay? So then I simply drop it. But the system depends on this. To emphasize that the interaction depends on the isospin, I put some isospin label for the interaction. Okay, isospin 0 and isospin 1, you have different interactions. Now, you find that for H bar interaction, H bar interaction, right? SVV interaction. You have only 2 different metric elements for each isospin. Only 2. Only 2 metric elements for 2 independent metric elements for each isospin. Okay, why is that? Because then this 2 is simply given by S Q bar 1 equals to 1/2, right? S Q2 equals to 1/2 because everything is 1/2. And then S Q bar equal to either 0. If this is 0, the other side you must also have 0. S Q bar 1 prime equals to 1/2. S Q2 prime equals to 1/2. S Q bar prime equals to 0, right? Because of the startup. Please. So it doesn't matter what kind of particle is exchanged. I simply assume they interact through kind of short distance strong interaction around the thresholds of these 2 particles. And then because around the threshold of these 2 particles, what does this mean? This means we consider energy range very limited to the very small vicinity of the threshold, right? And then the relative momentum is small. And then the corresponding length, the distance scale is large, right? And then the distance so large, and then it cannot probe anything inside this distance. So everything exchanged in that sense will be short distance. Of course, in some cases in reality, you would have some long distance exchange, for instance, pion exchange, right? But now I focus on short distance. Short distance, okay? The isospin is conserved, right? We consider isospin conserving limit. The isospin breaking effect is typically small, or the isospin actually, if in the isospin limit for when mu equals to md, we neglect electromagnetic interaction, and your Hamiltonian is commute with the isospin, so isospin is conserved. And then, of course, for each meson pair, you can have either in the isospin basis or in the particle basis. It doesn't really matter. And in this way, so it's kind of interaction, Right? I do not specify what kind of interaction that is. It's a kind of strong interaction. Strong interaction. Even if you have one-part exchange, this should also be similar relation. It's just in that case, you have more complicated structure because you have pion, propagator, all this stuff. But the conservation of all these spins are still there. Okay? I just, for simplicity, I simply write everything inside this operator. Now, this is one possibility, right? Another possibility is we simply replace this by 1. Okay, this 1. The second one is SQ bar 1 equals to 1/2. SQ2 equals to 1/2. SQQ bar equals to 1. Okay, and then SQ bar 1 prime equals to 1/2. SQ2 prime equals to 1/2. SQQ bar prime equals to 1. Okay, I didn't. Let me emphasize once again. I didn't write the SCC bar, right? SCC bar in principle can also be 0 and 1, but I didn't include that. That is because in the heavy quark limit, the heavy quark spin just decouples. It does not matter in which direction the heavy quark spin polarization is along, right? And then so this means for SCC bar equals to 0 and SCC bar equals to 1, as long as this is conserved, they give the same metric element. So I do not need to specify that out. Okay. Now this means we just have 2 parameters at leading order. Let me see there. Okay, I think I'd better remove this part. So this means at leading order of a non-relativistic expansion or a low energy expansion. So non-relativistic expansion. Non-relativistic expansion means we are expanding in parallel velocity, right? At the leading order, we have S-wave interaction. The leading order is just proportional to the velocity to the power of 0. It's proportional to constants. And we have 2. We can call this as contact terms. Contact terms. Or sometimes in the language of effective field theory, low energy constants. So in Juan's lecture, I think you can also learn or hear about the phrase of low energy constants, which are the coefficients in your effective Lagrangian that you cannot compute, or you must determine through fitting to data or from either experimental data or lattice KCD data. These are the coefficients in front of your operators. And these contact terms for each iso spin. Iso spin. Right? And then we can write this, for instance, as this one. We can define this as, for instance, Fi0, because this depends on the light degree difference total spin is 0. And this one is Fi1. Okay, I write this I explicitly because this depends on iso spin. Okay. So in this way, you can derive the interaction the interaction for each pair, for each H bar pair. For instance, for DD bar to DD bar, you can express the interaction for each iso spin in terms of these two constants. Okay, and for DD star bar to DD star bar, you can also derive a similar way. For D star bar, you can derive in similar way, and then you will find the interaction potential for D star bar to D star bar. Here, I refer to JPC equal to 1 plus plus. This means this actually is 1/2 D star bar minus D bar D star. Okay, we will find this for the given iso spin equal to V D star bar to D star bar for the same iso spin with JPC equals to 2 plus plus. Okay, you derive this, you can find indeed they are equal. Although without any derivation from here, we can already judge they must be equal. And you do the explicit calculation, you find they are indeed equal. If they are not equal, this means you have made a mistake. Right? So, but then this allows you to also express, for instance, DD bar to DD bar interaction and DD bar to D star bar interaction in terms of the same low energy constants or the same parameters. And then for each iso spin, this means as long as you have two inputs, and then you can predict 4 more states whether they exist or not, right? So that's how the interaction the simplest version as leading order can be derived, and Teng can show you more explicit derivations for the realistic system. But that's the basic idea. Any question up to this point? Yeah, please. What exactly D is? Now, the D is only specified by the spin. JPC equals to 0 minus plus is the pseudo-scalar heavy meson. We don't need to specify the internal structure of this one. The only starting point that we use is that inside this, the heavy quark spin is 1/2. The total angular momentum of the light degrees of freedom is 1/2. And the total spin of D is 0. So only this is used. And also, this D and D star, they are in the same spin multiplet. More question? Yeah, please. A V. You mean V? What V is? I thought it was D. Sorry. The V is so we don't need to bother about that. Or at very short distance, at very at very low energy around the threshold, right? And then this your low energy scale, low energy, which means your square root S, this is total energy in the center mass frame, is around the sum of is around the thresholds, right? The momentum is basically square root 2 mu square root S minus M1 minus M2, something like this, right? This is a non-relativistic momentum. So for small p, and then your distance scale. Distance scale is the de Broglie wavelength is the inverse of your momentum. It's very large, right? And then you cannot probe in this region what happens inside your de Broglie wavelength, right? You see, the happens all at short distances, and you cannot prove what happens there, and actually you do not care, because what happens here at leading order expansion of this non-relativistic effective theory are only constants. And of course, you can go to higher orders, and then this requires you to introduce momentum-dependent pieces, but then you have more parameters. But of course, these parameters you can still construct heavy quark spin symmetry relations, but they are more complicated. But you can go order and order higher. And then this order and order higher, this momentum dependence, this then proves to some extent what happens inside your interaction. Because it's just at this very near threshold region, then you do not care about your potential, what this really is. Of course, you want to go to higher energies, and then this becomes more sensitive to that. But then you also lose control of your expansion, right? So this kind of analysis, of course, only applicable in the near threshold region, and you have very good expansion. You have, so to see, you have separation of skills, and then you can construct their converge expansion. If you go to higher energies, and then you don't have convergence for the expansion, and then you lose control. Any more questions? If not, then in the very last minutes, we can talk about some similar systems, but also interesting ones, right? We go to the big news in 2015. That's the hidden charm pentaquarks. That's reported by RCB in 2015. In that year, they reported P sub C 4450 and P sub C 4380. So they saw one narrow structure around 4.45 GeV, and a much broader structure that needs to introduce to fit that data at around 4.38 GeV. This data is deep psi proton distribution. Because that's in deep psi proton final state, then the baryon number is 1, right? Because it's decays into deep psi, the mass here is about 4 GeV, and then we suggest that the structure, if this is really hadronic resonance, this should contain CC bar inside its structure. So that's why this is sometimes called hidden charm pentaquark states, because this should have at least 5 quarks or 4 quark and 1 anti-quark. Okay? And then in 2019, with the round 2 data from RC, the RCB, they just released a new analysis because now they have almost 1 order of magnitude more data points, and then they find that this guy is split into 2 finer structures, right? P sub C 4440 and P sub C 4457. And this one, they cannot confirm, or they can also not deny, right? But this was only introduced there to parameterize a very broad background in their data. Whether this is there, they could not make conclusion. But they find a lower one with a mass of 4312 MeV. Okay? So now at least There are three narrow structures. Narrow means the width of each structure is at most 10, 20 MeV. It's pretty small. Okay? But the interesting point is that this one is very close to sigma C d bar threshold, or below sigma C d bar threshold. Okay. The sigma C is 2455 plus 1870. I hope I'm correct. It's 4325, right? MeV. So it's only 10 MeV below this threshold. And these two guys, they are 130 and 140 something MeV higher than this one. But we know this darn D mass difference is 140 MeV. Right? It's around 140 MeV, slightly higher than the pion mass. So these two, slightly below sigma C D star bar threshold. The threshold is at around 4465 MeV. Okay. And the quantum numbers are not known. JP. It's a question mark, question mark. Right? But then, because they are close to the thresholds, and then there were suggestions that these are good candidates of hadronic molecules because they are so close to thresholds. And then when it could be interesting to study the S-wave interaction between sigma C and D bar, right? And we said D bar and D star bar, they are within the same spin multiplate. And sigma C is similar, right? We have another sigma C star, whose mass is above the sigma C by a few tens MeV. I think sigma C star, the mass, how large is that? It's 25, or who knows? I don't remember for this one. 25, maybe. Who can check? I think this number is wrong, but 25 something, around 25. Right. So it's a few tens MeV higher than the sigma C. So yesterday or the day before yesterday, we have analyzed the sigma C, right? We said this is CUD or CUU and CDD. What is the spin of this UD pair inside sigma C? Who still remember? Who know the answer? Yes. The spin of UD. How do we know the answer? Right? Of course, they can be either 0 and 1, but I asked. This means they should have a definite answer. So in the iso spin limit, UD are identical particles, generalized identical particles, and they are identical fermions. They must satisfy Dirac-Fermi statistics, right? The total wave function must be antisymmetric. The color wave function is antisymmetric because we have 3 quarks. And then they are S-wave baryons. So this means their coordinate space wave function is symmetric. So the product of the spin wave function and flavor wave function must be symmetric, right? This sigma c isospin 1, right? Isospin 1, the UD isospin wave function, which is the flavor space wave function, is symmetric, right? Symmetric flavor wave function, which means their spin wave function must be symmetric. And for two spin van half particles, symmetric spin wave function means their total spin is 1, right? The total spin of UD is 1, okay? This SUD equals to 1. 1 couples to van half. You have two possibilities. One possibility is G equal to van half, corresponding to sigma C. Another possibility is G equal to 3/2, corresponding to sigma C star. But their difference is only the different alignment of the heavy quark spin and the light quark spins. We put the light quark spins there. We just rotate your heavy quark spin. You come from van half to 3/2, right? This means these two guys are in the same spin multiplet, right? They are spin partners of each other. Again, the D and D star, they are spin partners of each other. Sigma C and sigma C star, they are spin partners of each other. So we can study this, the interaction between this spin multiplet and that Masonic spin multiplet, right? And of course, we can again list all the possible baryon meson pairs. For instance, we can have JP equal to 1/2 minus, right? This could come from sigma C D bar. Sigma C JP equals to 1/2 plus. D bar JP equals to 0 minus. And then, of course, they can form 1/2 minus. And then we can have, what's the other possibilities? Sigma C on this star bar, right? 1/2 couples to 1. You can have 1/2. We can have sigma C star, D star bar. 3/2 couples to 1. Again, you can have 1/2. And then you have JP equals to 3/2 minus. And then here, this guy in S5, you cannot couple to 3/2, right? But you have sigma C D star bar, and then sigma C star on D star bar, right? These can couple to 1/2. And then we have JP equal to 5/2 minus, and then you can have sigma C star on D star bar. I think I'm missing one pair. Which pair? That's exactly, thank you. Sigma C star and D bar. Thank you. We have 7 pairs, right? 7 pairs for each isospin. The isospin can be either 1/2 or 3/2, right? Because the sigma C isospin is 1 and D isospin is 1/2. Then we have 7 pairs for each isospin. And we can analyze in a similar fashion to see in how many spin multiplets these 7 pairs should be located in, right? So, who knows the answer? Or you can already know the answer from what I said before. You just generalize this to these hidden charm pentaquarks. First point. Heavy quark spins do not matter. Do not matter, right? So it doesn't matter whether your CC bar pair spin couples to 0 or 1. As long as it is conserved, it doesn't matter. And then what matters is the light, the total spin of the light degrees of freedom, right? And then we have two possibilities only. We have SQQ from sigma C equals to 1/2, right? From sigma C, equals to 1, as we just derived from sigma C or sigma C star. And SQ bar, SQ from the D bar equals to 1/2, right? It's from D bar. And then we have only two possibilities. These two, S, this is 3Q system. Because we consider S wave, there is no orbital angular momentum, equals to 1/2 and 3/2, right? We have only these two possibilities. This means at leading order, of non-relativistic expansion, there are only two parameters. Only two parameters for each isospin. Each isospin for these 7 pairs. The 7 sigma C star D star bar pairs, right? As long as we can find 2 inputs to determine 2 unknowns, and then we can predict 5 more. So using similar technique of the nitrogen symbol, you can derive relations for all this sigma C, D bar, sigma C star, D star, all this kind of scattering in terms of 2 parameters that you define from the measured elements in a similar way that I just erased for the D star instruction. And then among these 3 hidden charm pentaquarks, if you assume they come from this sigma C D bar, sigma C star, or sigma C D star bar instruction, you can choose any 2 of them as input, right? And then you can predict all the rest. It turns out that no matter which 2 you choose as inputs, there are always 5 more pentaquarks. Okay? So this means choosing 2 of the PC, the 3 observed PCs, 3 PC states as inputs. Because you can already imagine, because there are only 2 parameters, right? As long as the 2 chosen guys do not depend on the same linear combination of these 2 parameters, and you can predict all of the other 5, but because these 2 they both exist as hidden charm pentaquark states or molecular states, and then this means both sectors either spin the total spin of the light degree of freedom to be 1/2 or 3/2. They have attractive interaction, and then you can immediately predict all the others, right? And then 5 more. hidden charm pentaquarks. Hidden charm PC states. And one of them would agree with the third one that you didn't choose, which can be verified. Right? And then this means you have 4 more states, and it needs to be searched for in experiments. So far there is no very clear signal, but there is one in the data around 4.38 GeV. In the 2019 data, but much narrower than the one that they reported in 2015. Okay, in the data there is a kind of this kind of structure, which is followed by the very high narrow peak. So one cannot make a very solid conclusion statistically, but there is a hint for the existence at least one around 4.38. But of course there are 3 more generally expected around 4.5 GeV around this sigma C star D star bar thresholds. But there is no clear signal yet. We hope in the future with the round 3 data, they have a higher statistics. They can find clear signals, but we look for that. I think it's basically what I want to cover in the lectures. Okay, that's all. Questions? Yeah, please. So for globals, for instance, the difficult part is that in QCD, everything is inside hadron, everything is non-perturbative, right? There will be no pure global existing, right? Because everything, you can always create QQ bar pair, which can couple to your global system. And then there is no pure global. A pure global is only ideal object in your pure Yang-Mills theory. And then this makes things very complicated, right? And then in reality, it always mixed with other stuff, having the same quantum numbers. And then the question is, what would there be a unique feature that you can use to identify global? Which is not easy, right? Because how do you know whether this is global or simply SU3 singlet, SU3 singlet meson? I think this is as the core that why so far there is not a single state that one can unambiguously identify as global. Because it's an ideal object, but the life is more complicated. Yeah. No, there is one reported last year or the year before last year by base 3. It's called ETA 2370, which was supposed to have a large gluonic excitation. But I think there is no model independent conclusion, but there are some hints from some theoretical calculation. For instance, there are calculations considering, for instance, gluonic operator when compute the spectral function created by the gluonic operator. And at some point, it has some excitation around 2.37 GeV. And the ground state actually is even lower at 1.7 GeV, somewhere around that. This calculation done by Xiaonan Li from Taiwan. And of course, there are some also lattice calculation, but the lattice calculation, the most well-known ones, they are still quenched lattice calculation. This means they did not consider the mixture of gluonic operators or the gluonic object with QQ bar, this stuff. So it's not very realistic. And then in a full dynamical QCD, And then the question now again comes to what is a global, right? What would you identify as global? Actually, the complication also comes from even if you use Gronik operator, you compute something, this does not mean that guy is global. For instance, if you can use Gronik operator, G tilde, to compute eta prime, right? But we do not call eta prime as global. We do not call eta prime as global. Right? Yeah. You can see it has this Gronik components inside, but then the question is, what kind of state you can call really as global? Right? This is I don't see an easy answer. But of course, people are still trying to identify. The hope is that maybe some states are really dominated by Gronik operator, but I think the difficult part is what would be the unique feature? Right? What would be the experimental smoking gun to let you identify the dominantly Gronik component state? So the nice thing for the heavy quark stuff is that you have heavy quark approximate symmetry. You have certain relations. And then you can have predictions that can be falsified by further experiments. More questions? So if not, then let's have a break.